In this video, we'll generate the Legendre polynomials using Google Sheet functions of multinomial and combine, where the values of k is from 0 to n and the value for n is from 0 to 10. So data validation, list of items 0 to 10. And here are values of n all the way from 10, 0 to 10. And our value for k will be sequence of n plus 1 column starting from 0 incremented by 1. So that if n equals 0, our k value is 0, and if n equals 1, our k values would be 0, 1, n equals 2, k value 0, 1, 2, n equals 3, k value 0, 1, 2, 3, n equals 4, our k value 0, 1, 2, 3, 4. Next, we enter the series sum formula, which is array formula, series sum of the quantity x minus 1. So x minus 1 over 2 raised to the power k, where k starts from 0, incremented by 1, and the coefficient will be this range. Now we can continue with the coefficients using multinomial and combine functions. So this is equal to multinomial and comma k times combine and comma k. And we lock the reference. So we have here our reference of n is locked, D14 and D14. D3 will not be locked because it moves as we copy along the column. Then enter. As we drag this, we have an error. If this is empty, this should be 0. So we'll correct that. So start with this. We'll go back to the formula. If D3 is empty, then 0. Otherwise, calculate. Enter. And we drag this. Now it's corrected. Then we chart this using scatter chart. Insert chart. And we'll use scatter chart. We use scatter chart and enter the trend line using polynomial to the 10th degree. And use the equation as label and move it to the left. Make it more visible. Font 16 will do. And this should be okay. So here we have the trend line equation, the Legendre polynomial using the chart. Next, we calculate the coefficients using LINEST. To do that, we will complete the 1 comma x matrix, which is equal to array formula of the x values raised to the power 0 to 10. Enter. Now we can enter LINEST data y n dot x. So we go back to the value of n equals 0 and compare with our regression coefficients. So start with 0. At n equals 0, our polynomial y equals x. At n equals 1, the Legendre polynomial y equals 1x. So at n equals 0, it is 1. At n equals 1, it's 1x or x. N equals 2, that's negative 0.5 plus 1.5 x squared. So negative 0.5 plus 1.5 x squared. N equals 3, that's minus 1.5 x squared, or x, plus 2.5 x cubed. So negative 1.5x plus 2.5 x cubed. N equals 4, that's 0.375 minus 3.75 x squared plus 4.375 x to the fourth. So 0.375 minus 3.75 x squared plus 4.37 x to the fourth. N equals 5. Our polynomial y is 1.875x, 1.88 minus 8.75x cubed plus 7.875 x to the fifth, or 7.88 x to the fifth. N equals 6. Our Legendre polynomial y is minus 0.313 plus 6.562 x squared minus 19.7 x to the fourth plus 14.4 x to the sixth. N equals 7. Our Legendre polynomial y is minus 2.19x, that's 2.19x minus 19.7x cubed minus, that's 19.7x cubed minus 43.3 x to the fifth plus 26.8 x to the seventh. At n equals 8. Our Legendre polynomial y is 0.273 minus 9.84 x squared plus 54.1 x to the fourth minus 93.8 x to the sixth plus 50.27 or 50.3 x to the eighth. N equals 9. Our Legendre polynomial y is 2.461 or x minus 36.1 x cubed plus 141 x to the fifth minus 201 x to the seventh, that's 201 x to the seventh plus 95 x to the ninth. N equals 10. Our Legendre polynomial y is minus 2.246 plus 13.5 x squared minus 117 x to the fourth. This is 352 x to the sixth minus 427 x to the eighth plus 180 x to the 10th. This completes the use of multinomial combine in Taylor-Maclaurin's series expansion of the Legendre